Okay. So I'm going to talk about this work, which was published few months ago, but it was actually done like 3 years ago, and we went through several rounds of refereeing different reviews. And since it's a mix of experimental and theoretical work on spin glasses, it was actually the referees had a very hard time understanding what was going on. At certain point, one referee, I hope it was an experimentalist, complained about the fact that you cannot have more than one Lagrange multiplier. So, so that was like, oh, it's not true. You can have as many as you want. Anyway, okay, so that's the reason why. Now, recently, I saw there is some activity exactly on this topic here. There was a paper couple of days ago, maybe like a week ago or so, by Mike Kolodrubets. We are thinking actually with Paola Capellaro and Nicole Fabri. Paola is at MIT and Nicole is at Lens in Firenze, where also Santiago and Ana Gomez did his PhD, then went to MIT and now is back in Firenze to organize a meeting on this topic next year. So if you're interested, just look for it. So the idea is the following. We want to have a quantum sensor. Okay, so a sensor that beats the classical limit to measure in this particular case magnetic fields. Okay, how do you do that? So first of all, you need to have very good control over this object. It has to be a bona fide quantum quantum object that can be in a superposition of states. And in particular, for these experiments, and I refer you to this review of modern physics by Paola and other two important experimentalists on this topic, which is quite recent, and it has all the details of calculations for the basic formulas that you are going to use. We considered NV centers. Okay, what are NV centers? NV centers are, you take a piece of diamond, okay, and then locally, this is a vacancy. And next to the vacancy, there is a nitrogen atom. Now, this system behaves as a spin with the magnetic momentum, okay, that can be addressed using microwaves, and you can read, because of photoluminescence effects, the state of this spin, okay? So the experimental details are fantastic. They are, I mean, I'm probably not the best person to describe them to you. If you want, you can go read both our paper and the review of modern physics. For what I'm concerned today, the idea is the following. Oh, hey. So you have a two-level system, okay? You initialize in a state, you evolve it, and then you project back. Actually, since the evolution is not unitary, because there can be decoherence, okay? Let me just, and then you read the survival probability, okay, after a certain time. And this thing is, there is a decoherence function here, which yields the signal. And the idea is that you create the system in the X in this superposition, which is directed along the X axis, okay? And then you want to measure a magnetic field around the z-axis. So this makes the spin in the x direction precess, and then you redo another pi half pulse, and you measure the survival probability. Okay, so this is a measure of the phase accumulated by the system, which is given only by the field around the z direction that you want to measure. Okay, so you start with an initial thing, then you do a pi half pulse, and this creates a superposition. Then there is some evolution here, then you do a pi half pulse here. And then you do it. Okay.
But what you're trying to sense is basically the magnitude of the field.
Exactly.
Right, so you're trying to see how you're trying to read off the angle of precession from that. So the field is supposed to be very slow on the time scales of everything else.
To begin with. Now we are not going to suppose it to be slow anymore, so we need to modify this and act with pi pulses. Okay. Now, pi is just the phase accumulated, so there is some, magnetic perceptibility, then there is the amplitude of the field, and then the field B of t, let me call it like B, and then there is an H of t, which is just, this is like between -1 and 1. Okay? So B is the maximum over the experimental time of the amplitude of the field. And this is what the order of magnitude of the field. This is what we want to get. So, and the phase is going to be this, right? Now, if H is a constant, 1, okay, so the field is a constant. This is all fine and well, right? We can measure this phase. It's going to be a monotonically increasing function of t. If you forget about the periodicity of this thing, so you don't run your experiment for too long, you're fine. However, if you have a time-dependent signal, in particular an oscillating signal, then if you accumulate phase longer than the half period of the signal, then it's detrimental. Okay? This integral will just be small. This integral will be essentially 0 if I take it sufficiently long. So what can I do? Well, if you now, let me, this goes back to 1950s. If you do a pi pulse here somewhere, then you are the contribution of the phase that you're getting gets a sign reversed. Okay, so suppose this is your experimental time, and then at time t half you do a pi pulse. Then what happens is that the phase up to t half is this, and then from t half to t gets a minus sign. So now, for example, if you have just one oscillation, okay, you can accumulate a lot of phase. So this is your experimental, the duration of the experiment, okay. If you now do a pi pulse here, then you're gonna get essentially the signal reversed. You gain much more phase, and you can measure much smaller fields. Okay? So this is the idea of having so you have control over this piece of diamond, and then the experimentalist, in this case, the good Santiago here, does a sequence of pi pulses, which are supposed to be at the right moment to accumulate more phase. So even if the field is now going in the opposite direction, you do a pi pulse, now your spin is around that, so it takes positive phase as well. Now the question is, when should you do that? Okay. So if this were the only thing that depended on the pi pulse sequence, okay, Well, it would be clear, right? Whenever H changes sign, you do a pi pulse, and then you accumulate more phase. However, the decoherence also depends on the pi pulses. Okay. In particular, now let's define a function y.
Sorry, I think
Yes.
I got lost. So H, that trace, that's the signal, you're trying to now measure not DC magnetic field, but AC magnetic field.
Yes, you want to measure this. Let's set this to one. This quantity is a property of the MD center, so we don't care. You want to measure this.
But
Okay.
H of T is a pure cosine, or what do you know about?
Suppose
H of
that
T?
it,
What do you know about H of T?
for the moment, H of T is any function. What I'm telling you that in general, if it is a function which changes sign,
Right,
you want to do a pi pulse where this function changes sign.
sure.
Okay, in this way you accumulate positive phase and you can measure smaller b. The larger this is,
Well, yeah, I guess the point, what I don't understand is that if you're not measuring the full function.
what do you
then
mean
you're-
measuring it for,
No.
what does it mean to
Well,
measure it?
because you can, suppose you have time result EFT, you can measure, you can, in principle, if your capital T is variable, you can measure the integral and you can take a numerical derivative and you're done.
No, okay, no, that doesn't work
Maybe I
actually.
don't understand what.
No, because,
if H is a constant, then I totally understand what the measurement is. You know, you just see a linear increase in
Yeah.
the phase. If H is not a constant, well, you see an integral of H. So you could, if you map it out.
no, that's, no,
No.
okay,
I
so
think I told
the goal is not to measure the integral of H, the goal is to measure the amplitude B.
But if you don't measure H, okay, right. If you don't measure H, you cannot sweep H under the rug.
Suppose you know exactly the form of H.
Okay,
How do you measure B?
fine, that's a different question, but.
This
you
is the
know
question
that-
experimentally studying
Okay,
today.
but how do you know the form of H,
You know the frequency typically of the signal.
but not the amplitude?
Exactly.
Ah.
That's what you want to measure. That's exact. Suppose you know the form of H. You want to measure B.
Right.
And you want to have a protocol. Now we understand that if
I-
H changes sign, you have to do something like
No,
pi
I understand
pulses.
that, yeah.
Okay.
There's, in NMR, there's all these pulses.
Exactly.
Yeah, okay, Haneko, I mean, you're basically describing a Haneko.
This is exactly how I, yes, on 1950.
Yeah, usually I don't think of Haneko. Except for a picture where you have the circle where it goes around and you flip it to catch up.
Yeah.
Yeah, okay,
Now you want, now Haneko, there is a protocol where, when to do the pi pulses, right? And this, depending on the form of H of T, this protocol needs to be found. So the goal in this paper is to show that this optimization, given the form of H of T, is an optimization of spin glass, essentially. And we devised a couple of algorithms that actually outperform anything else.
okay.
Okay. Now, if you ask what's the sensitivity is the smallest field that you can measure. Okay.
So just to understand, there's no many body physics, it's just, the issue here is that the time domain. Optimization is.
Becomes a many body
it's one of
problem.
these, I remember there was this, Pontryagin functional or something like that, you can define the minimization procedure has some kind of free energy associated to it. Is that-
Yeah, this is
That's
what
what
I'm
you
gonna
talk about. Okay, got
write
it.
down
Thank
now.
you. Sorry, I don't wanna.
Very good, very good. No, I mean, we can use the fact that this is a very small audience and take our time. And sandwiches are gonna arrive at certain points, so you know, the longer there is also reward at the end, so.
Yes.
So, the thing is the following. So the sensitivity, you can prove that the smallest field that you can get, there are two ways to do this. They give equivalent result. You either define the Fisher information or just the, you know, the derivative of the P of T with respect to B. Let me not do this calculation because it's 3 lines. Yes, I haven't told you. So if you have now, okay, so my pi pulse sequence defines a function y of t, which is positive and changes plus 1, changes sign every time there is a pi pulse. Okay, so y of t is a map from 0t to -1, 1. Okay, whenever it changes sign, there is a pi pulse. Okay, so my phi now has a y of t here, and chi also has y, but remember that chi comes from the noise. Actually, remember, I didn't tell you. So chi comes from the decoherence noise of the everything that is going on in the diamond. Okay, and you can write this as 1/pi the omega s of omega. Well, s of omega is the spectral noise measured in the diamond times the Fourier transform of the square. This is obtained experimentally. It's a characteristic of the sample. And I can also write it in the time domain. Where j, t prime, t minus t prime, t, it actually depends on the difference, but let me write it like this because then it looks like an operator matrix. It's the Fourier transform of the noise spectral wave function, the spectral function, which is the autocorrelation function of the noise. Okay. Now, what you know is that although this is positive, this function here is not necessarily positive. Okay. So eta is square root of t e to the chi of y is a quadratic function of y, and then you have integral between 0 and t dt h of t y. Okay. Now this eta is the smallest field that we can detect in an experiment with which lasts square root of t time, okay, and as a signal h of t and a protocol y of t. So what we want to do, we want to minimize this thing over all the possible choices of y of t given an h of t. That's our task. You can take, this is dimensionless, this is if you divide this by t, this also is dimensionless. So now we have, and then we take the logarithm, and this gives us a functional that we need to minimize. An energy functional, okay, which is 1/2 integral dt dt prime y of t j dt prime y of t prime minus log of 1/t integral dt h of t. Okay. These under the constraint that y squared is equal to 1. Okay. So what do? We add a Lagrange multiplier.
Wait, hang on, can I just understand? So, what is y? Sorry, I forgot what y.
Again, y is the function that when it changes signs, it tells you that you're doing a pi pulse. So for any pi pulse sequence, there is a function y. Starts with 1, and then pi pulse changes sign. Pi pulse changes sign. Okay.
Why do you have to do that? You just chose it based on the intuition.
Because we say that when you do a pi pulse, the contribution to the phase from that point on is reversed.
But there's some wiggle room. You can do the pi pulse close to, but not like, in the interest of optimizing, if you give yourself more freedom where to do the pi pulse, it seems like there, I understand. So by doing this, there's a there's no choice where when you make a Y, so it becomes kind of just a spin flip.
Y is your choice.
But you already made, no.
Because are you optimizing over like when you do the pi pulse?
Yes,
And also
exactly.
how many is that?
Yeah, exactly.
Right.
So you're optimizing over this set of functions y, which such that y squared is equal to 1. And this set tells you when and how many pi pulses you do. For example, the function y equal to 1, you don't do any pi pulse.
Right.
Then y changes sign at a given point time
Okay,
T1?
so fair, misunderstood. So the flips, the pi pulses are not tethered to where H crosses.
No.
Right, good.
No,
Fine.
this is
Yeah, no,
a general function, and you want to find the minimum of
Okay.
this. So you want to find the minimum of E of y subject to the fact that the function is either 1 or -1.
And you don't really care that the pi pulses are not gonna be perfect, because in the presence of H, your ability to, in
Mhm.
physical terms, the way you make a pi pulse, you put a resonant AC
Yeah.
field to flip it. That means you need to know the resonance condition, and if you have a time dependent H, your resonance.
H is small here. So
So-
then this
so
is
the
about
quality of
you
the
want
pi
to go
pulses
you
is-
want to go to the smallest detectable fields.
Right.
So your pi
it
pulse
becomes- yeah, yeah.
fields are gigantic with respect to that.
Right.
So that's not an issue
So
in the
that's,
experiment.
yeah, so the quality of, in the regime where you're interested, the
Exactly.
quality of your pi pulses is not.
It's
gonna be
perfect. It's not.
Good.
And also, we can also tune the pi pulse in such a way. So in general, this also depends on the signal, right? But the signal is, we are in a region in which, a regime in which the signal is very, very weak, so it doesn't really matter. So the approximation really, I mean,
Anyway,
the
yeah, I'm
experimental.
fine with a perfect pi pulse approximation, but that's, okay, continue. Thank you.
So what you do, you add a Lagrange multiplier for every point in time. Which pisses off some referees apparently. Okay.
That's between you and your referees. We don't need to.
No, I keep telling it around. You never know. Maybe there is the referee somewhere.
Oh, if you have to keep looking at the audience, if the referee turns red, then you know that there's a response.
Say it again.
If your referee happens to be in the audience and you can make fun of the referee, the face turns red.
Exactly. I'm looking for a reaction. Yeah. No, but I think this must have been an experiment. Okay, good. So now you have now what do you do? Now the physicist, the theoretical physicist has to kick in and start taking functional derivatives, right? There are two things. dE by dy is equal to 0.
Wait, can I ask a
Yeah.
very quick question? So, are you gonna assume some types of JFT T prime? Some
No.
kind of a,
So far, the only
So the
thing that I
nature of the
assume
dot
about
doesn't
J is
matter.
that a positive operator. Because it comes from, it's a positive operator, this.
no, S is a positive, but J could have, as you said, they could have
Yeah.
oscillations, but usually like in the, yes, the usual sort of a spin boson problem, J is a power law function.
No, we don't do that. Actually, what we are gonna do to compare with the experiment is to extract this S of omega from the experiment
Right.
and then do for it.
But it's not a famous like one over F
No.
or anything like
No.
that. It's-
No. It's dictated by the experiment, and so far it's completely generic.
Okay.
The only
No,
thing I
understand
want
the
is,
formalism, I'm curious, like, okay, anyway, continue. Yeah.
I mean, what we did is that we actually were very focused on the experiment in the sense that like we have this thing for which we know the S of omega, we know which kind of fields H of t we want to get. How can we push up the optimization, the optimal thing? Okay. So this thing is from here, it has a linear part. J t prime plus lambda of t delta t minus t prime, everything multiplies by y of t prime, and then there is the logarithm that gives you h of t divided by integral 0 d t prime h of t prime y. Okay. So you need to solve this, and you solve this. To remind you that E is log of eta normalized. Good. So you can solve this if you just write. Let me solve this. Y is equal to 1 over d, and now I'm going to tell you what d is. dt prime 1 over j plus lambda, which is this operator here, dt prime. Okay. H of t prime, and then d is integral of yh. Okay, and if you substitute again this equation here, you find that it is 1 over d integral h 1 over j plus lambda h. Okay, dt prime. Okay, so this means that d is the square root of this thing. So it's a nonlinear equation, but you can solve. So there is a formal solution, which is this. Okay. There is a small caveat. We don't know what lambda is. Okay. So lambda need to be chosen in such a way that this thing here is either +1 or -1 at every time t. Okay. So there is a formal solution, and there is also a E of lambda at y equal minimum, which is also the thing which will be 1/2 minus log of this thing d divided by t minus 1/2 integral dt lambda d. Okay. So again, this is a formal thing. You could also decide to look at the minimum of this thing with respect to lambda, which is, and then to get that. But there is again a problem, because now this will solve some equation which is very similar to y. So there is a duality between y and lambda. And unfortunately, there is conservation of difficulty. So
this lambda is just a Lagrange multiplier.
Lambda is just but it's a function.
You know, sure, but the idea is that I should imagine that there's a profile of h of t. And out comes out, and out of this, you need to solve for lambda of t.
Yeah.
And you're done.
Yes. Okay. So
Sorry, but where's the equation for lambda of t?
take
It's
this
an
and
implicit
take
equation.
dE in the lambda is equal to 0.
Right.
This contains lambda.
Right, exactly. Okay, and it's a functional, it's, yeah, it's some kind of a,
It's a functional equation. It will be an integral equation for
it's
lambda,
an integral. I
as
don't
it was
take
an integral
derivatives.
equation for y.
It's a purely integral equation, there are no derivatives.
It
Right.
depends how I think if you can approximate this j properly, you can turn this integral equation into the derivative equation.
Right, PD kind
A
of,
PT, yeah.
but PD or OD? It's a nonlinear OD. I'm just trying to like classify this problem, I don't. It's a nonlinear OD. Okay,
It's a non-linear already,
that's fine.
but yeah,
In one dimension. No,
yeah.
doesn't seem very, okay, you're
I
gonna tell me.
mean, the form of J of T that comes out from the experimental profile,
Yeah.
noise profile, didn't to us look particularly simple that we could actually do things. Like, for example, J is not Gaussian, it actually changes sign. And when when you do these kind of things, you have derivatives with opposite signs.
Right.
Okay, and that looked bad. So there are we devised two possible alternatives, okay, to actually make progress in this direction. So there are two things you can do. First, at least two things that came out of our mind. First, you relax the condition that y squared is equal to 1, and you replace it with something simpler. For example, that the average is equal to 1. Okay, you can actually improve this thing, saying that, you know, divide your interval in two, the average here and the average here is equal to 1. Okay, which doesn't mean that they're separate. I mean, this thing is a loser condition. You can go to 3 intervals, 4 intervals. It's like building your Lagrange, it's saying your Lagrange multiplier is a constant in this case. Here it's like 2 constants. It's the same thing. Okay, good. So you can improve this thing step by step to get to the continuum limit. If you do this, however, now your Lagrange multiplier is a constant. And then it's easy to solve this problem because it's just now it's a function of one variable, this thing. You can do all the steps here and then put lambda a constant and do that. And we call this solution the spherical model solution because essentially you replaced your spins with the average spherical model. And this actually gives an upper bound to the sensitivity because we are optimizing in a larger space. We optimize the same functional in a larger space. So the minimum is going to be better. And so the spherical model gives a sensitivity which is an upper bound. Which is a lower bound. Okay, it's a minimum, so it's smaller than whatever you can achieve in a smaller space. And when you do this, you actually get that all the experiments are below this line, not that much below. Actually, what we did also, you can get, so we actually think that this is essentially sharp as a minimum, even though it shouldn't be that much. If you, for all the profiles H of T that we looked at, when you, for example, do the 2 Lagrange multipliers thing, you gain like 2% over the bound. Okay, so you cannot really improve too much. So there's a sequence of bounds.
Is there a formula for A to SM? In terms of S
and H of yeah,
and,
yeah.
I think mostly just T, right? Because the longer you wait, the worse the problem gets. I'm trying to ask what.
There is a compensation. There is a compensation.
Right.
The longer you wait, the more phase you can accumulate, but then the worse the problem becomes.
Right.
Okay, so there is a compensation there.
I'm just trying to like ask what kind of like interesting scaling behaviors, even because A to SM becomes kind of like an extended.
Okay, let me actually.
Curious, like if there's an answer, it'd be nice to. There.
Oh no, you mean?
you solve it analytically, I guess I'm asking.
It's analytical, but again, it's a functional of oh, you
Yeah, we could,
you can, yeah,
you guys
you can,
see it on
you're
my
seeing it on Zoom, right?
Not on.
Oh, you can see it on that side. On this side.
Okay, so yeah,
Well, no, they can see it on my screen.
okay, very good. So let me show you. Let me show you, for example. Let me show you this thing here. Okay, the upper bound is this spherical model approximation, this dashed line here. Okay, and all the other, this is experimental data.
Right, it's a function of T.
It's a function T. You see, this is the part in which it actually goes up,
Yeah.
and then and these are pretty good sensors, right? Eventually, it goes down. Okay, but we don't see that.
Yeah.
Okay, so this line here is the upper bound. Now, these red and orange things are called Carpur-Cell, and it's a protocol for the Anseco experiment in which essentially every time the field changes sign, you change sign. Okay, and you see that it doesn't do as well as the blue line, the blue dots, and the blue dots I haven't yet told you what they are. Okay, the blue dots are the second approximation that we do. And the second approximation.
Can you help me be oriented about this? Is like, you want this numbers to be lower?
No, this is 1 over eta. This is you want eta to be lower, but you see on the y-axis is 1 over eta.
Okay.
So you want it to go
So spherical would be ideal, but you can't really do it.
Exactly. You cannot achieve that.
Okay.
But the point is, okay, good. I think the Carpur-Cell was the one where you basically have an antiferromagnet of these pipe pulses. Like basically they're organized to zeros of this H. And what you're saying is that the spherical model or whatever it is that you're playing with allows you to, it's like you know, the neural spike train. You're designing a spike train to
kind of so the idea is what you were saying. So H is in this part of the Hamiltonian, right? So if these were not there, what would you do? You would just get this as large as it
right. Without J, the Carpur-Cell is correct. You're
Exactly.
actually the fuzziness introduced by H, you're optimized. Okay.
Exactly.
Oh, this is nice. Okay.
So without without J, the Carpur-Cell is correct because H will change time. Remember that H is between -1 and 1, in between -1 and 1. Okay,
Right.
H is also between -1 and 1. What's the maximum here when Y is equal to H?
Yeah, you're just canceling those.
Okay, so and that
Nice, okay.
that gives you now you're dealing with when you do this, you are getting some contributions from J because J say, okay, you want to do that, but actually the noise will tell you that at that time distance, the things want to be anti-correlated. So this should actually be up. So if you combine the two effects, now you have this thing here. Okay. All right. So this is what I was saying. So this is the spherical model with one Lagrange multiplier. Then there is a sequence spherical model with two Lagrange multipliers and so forth. And then there's the real deal, right? And what I'm telling you is that we did this, and you move away from this by like 3%. So there isn't really much room in here. This is already very good. So let's do the second thing. The second thing is, as Katz used to say, be wise, discretize. So take your function y and just discretize.
The KAC cuts?
Yeah, I taught by Larry Schulman. I'm not sure as I haven't heard. So y is now you discretize it, right? So y of t becomes and this is the indicator function. I delta t, I plus one delta t.
Right, what do you just, that's what I do.
So take your function, okay, and discretize the time in interval delta t,
Yeah,
and then these now are spins, plus one, minus
Yep.
one,
totally, yeah.
plus, okay? Now this becomes now a function of spins, right? And it's one half sum over I in j, si j j s j, minus log of sum over I, hi, si. The only thing you have to be careful to keep the delta t square here, delta t here. So it's,
Like, could you stop the
and now you
screen?
have a spin model, right? And you could do simulated annealing, for example, in this. Well, in the interest of time,
So, but lambda is still floating around there. So you-
no, now you don't need lambda anymore
Why not?
because this automatically satisfies the thing. These spins are plus or minus one.
Okay.
You don't need lambda anymore.
Right, right.
Lambda was to enforce y to be plus or minus one, right? Now you have spins and you flip the spins.
Right.
And when you do this, probably this will stop share for a second in case they want to see the back.
Yeah,
And when you do this, there are a couple of caveats that you have to do. So first of all, you could do just simulated annealing, okay? Nice thing. Start from an infinite temperature spin configuration and just minimize with respect to this Hamiltonian, reducing the temperature.
do you even have to do simulated? I mean, where is the disorder here? Like, why couldn't you just like greedily find the ground state?
You could do that. That's simulated annealing in which you switch the temperature right off to zero.
Right.
Okay. There is an issue. You get stuck.
Yeah,
into
that's
minimum.
why, like, what's the physics of this?
This is both ferro and antiferro
I see.
and long range.
Yeah, it is long range.
So it's not really one
Yeah, yeah.
dimensional.
Good.
Okay, so and what's and
But it
what's
is
happening-
long range because of the property of the noise. It's
Yeah,
kind
the
of
correlation time of the
contrast
noise. Yeah. If the correlation time of the noise was extremely small, then this would just be.
That's-
Um,
So if the bath is at high temperatures, there's no issues of how to do this.
Yeah.
Because that would be a short correlation time.
what would be a short?
The bath, basically the property of the bath is. I felt that the correlation time of the bath becomes longer as a function of temperature.
You're talking about real temperature here. When I do
Yeah.
simulated annealing, it's fake temperature
No,
to
no,
find
I
the
mean,
minimum of this
properties
thing.
of J comes from the property, the spectral.
Yes,
Form
yes.
factor of the bath.
Yeah, that
And then that's
I mean
temperature
the object is at room temperature.
I see.
Yeah, I mean the experiment is done in a room like this. I've been there many times, and there's one
Yeah, okay,
air
fine.
conditioning thing, and that
Yeah,
you
no,
can
okay.
see when you go from like 22 to 25 Celsius in the room that things change a little bit.
Yeah, like,
So there are sensors to make sure that you are working at the same temperature, but it's done at room temperature.
the
And the idea
physics-
is that you could use this also in biological.
no, I understand that. The point is that in physical models of the bath. To get really nicely long ranged, this sort of, I'm talking about the spin, caldera like, 1 over t squared. There, the bath has to be at zero temperature to get that parallel long range thing. So here, I don't know what the bath is, so never mind. Tell me.
But is the phonons in the diamond.
Okay, so they're probably.
They're pretty
parallel
stiff.
because-
Yeah.
But they're also parallel. They're probably.
They're-
Those phonons
yeah.
are at room temperature, they're at zero temperature.
Yeah, exactly.
Okay, I got it. So goodbye temperature. Right?
Yeah, yeah.
Okay.
Okay, so now you look at the minimum of this object, and then you see that simulated annealing doesn't work very well. It gets stuck in this minima. In particular, I mean, you need to run it for a very, very long time in order to find a configuration which doesn't have too many pi pulses. And you know that you're not, I mean, too many, what's too many? It's too many with respect to our experience with the other thing that I'm going to tell you. So but we found a trick. If you use the spherical model solution as a starting point for the simulated annealing. So what do? You get this y of t, which is solved by analytically by testing. So you find your lambda, then you find your y of t, and then you have to project it down. Let me show you on.
Can I just ask a very quick dumb question? So
Yeah.
the number of spins is essentially setting your delta t.
Yeah,
That's not real physics. That's just your method of solving.
yeah. Yeah.
So somehow intuitively, what you should be doing is you should be looking for solutions where the number of pi pulses is independent of the number of spins. Because number
There
of
is.
spins is not physics.
There is. So if you really solve this thing here, then the if you see that this is a non-extensive Hamiltonian, it's non-extensive. This is log of something.
Yeah.
So there is no scale. This energy doesn't scale with the number of spins, exactly because of that reason, because there is an optimum number of pi pulses, and you could decide to discretize this with, I don't know, like femtoseconds. And then when you minimize this, you would say like plus forever in mind. So
All right, fine. Okay, good. As long as that's.
in fact, I think the thing that the spherical model does, it captures approximately the number of pi pulses that you have to get.
On average.
And then the optimization moves the walls around. This is more or less what,
This is how the experiment ended up winning over the spherical model.
say again?
The picture that you showed before about the experiments actually did better than the spherical model. This is how you.
Worse than the spherical model.
Oh, worse.
Because
Sorry,
one over
sorry,
it, yeah. So this is what I'm saying. So you start, this is the blue line is the solution, analytic solution of this spherical model. And then you project it down to this plus or minus one, just by taking the sign, take the sign function of that y of t, and you use that as the initial condition for the simulated annealing. And then you do simulated annealing for like, I don't know, like 20 steps essentially. So you could even do a greedy algorithm there. It works so well that the previous optimization that they were doing, Paula and Nicole, in the previous work, it took like 1 day of computer time on Mathematica to do optimizations. And we ran the code on a Raspberry Pi for like 0.02 seconds, and we found a better.
Raspberry Pi.
Because we wanted to we want to show that actually don't need much computational power. And also Raspberry Pi is, I had the Raspberry Pi, I wanted to play with it. So I wrote C++ code Raspberry Pi and works that outperformed everything that was done before. So when you do this, you get these blue lines here. Actually, okay. Now let me show you this picture first, okay? Now we did an ensemble of signals H with some specific characteristics. So there were like 7 frequencies, randomly distributed, and then amplitudes randomly distributed, and phases randomly distributed. So we had an ensemble, and we ran Carr-Purcell. This is generalized Carr-Purcell, is what I was telling you. I mean, do a pi pulse when the field reaches sign. Carr-Purcell is slightly different, in which it works for a field which is like a single frequency, and so you do pi pulses at that frequency. But in general, if h of t is as many frequencies, you decide to do the future. And you see this is now goes within 20% of the upper bound, instead of being like 50%. But the important thing is that the fact that you're actually optimizing, you're taking into account the presence of the noise, keeps this thing stable as a function of time. Okay, so this is 85%, but it's 85% for like 20 microseconds, 30 microseconds, 100 microseconds, while Carr-Purcell or anything that doesn't take into account the presence of the noise is going to be down, it's going to go down with time. Okay. Good. And if you do this in the experiment, then we did the experiments with the sequence that came out from the numerical optimization. And this is the blue lines, the blue dots. And so theoretically it will be, I think it will be this thing. Actually, the experiment actually outperformed the theoretical prediction for some reason, which we don't know. Maybe we overestimated something. And yeah, and the other ones are below here. So it's okay. This is the derivation of this formula, the first formula that I was telling you. I'm not sure there is anything else. These are more details about the experiment. Yeah, that's it. So, yeah, so if you do optimization properly, either numerically guided by, it has to be guided by this thing here, I have to say. And if you just did the numerics with similarity annealing, you would find the result, but numerically takes the algorithm takes a lot of steps to do that. Instead, if you guide it by the here, I guess the reason for this is that really the solution landscape is not that complicated.
Yeah.
Probably there is like it probably is similar to that source thing. Like there is one minimum. Okay, and then there is a lot of stuff up here where your simultaneous annealing gets trapped just for lack of time of finding the golf hole, right? So if you are ready, if you have a way of dragging down already the initial condition to close to the basin of attraction of the solution, then just boom. Yeah. This is everything I wanted to say.
Okay, so, well, let's thank Antonello, but we have questions, I think.
As I said,
And most importantly, the food is not here, so.
yeah, exactly. Unless until the sandwiches are here, I'm not gonna move.
Right, okay, I have a bunch of questions. Maybe
Just as an optimization thing, did you consider also, there's only so many pulses, so you say, pick the number, like 7 pulses or something, and then you just parameterize those 7
Yeah,
pulses.
that's what Nicole and Paula did before.
Oh, okay.
So it was like a function. They picked like, I don't know, like 20 positions times, and then they optimized the functional of these 20 variables. Now that's continuous optimization.
Yeah.
And it was a disaster.
Okay.
I mean, they had the paper 2020, I think, in which they did that. They found some results, but the computational time was like a day on a cluster.
Just using some kind of like.
I think MATLAB.
Yeah,
Exactly. Just some nonlinear thing in MATLAB. And that's exactly how the thing was born, because I was visiting Firenze, and we were discussing about this thing. And I said, well, maybe, if you discretize this thing, it could be a spin system, and we know how to do that. But that's the first thing they did, and that's much more computationally demanding than this thing.
Like the landscape must just be worse or something.
Exactly. Yeah, also because when you have continuous optimization of continuous variables, it's better if you know like the derivatives analytically, and here you don't.
Oh, okay.
So it's a mess. So you just have to give this thing to the computer, and the computer has to guess in which direction. I mean, you have maybe to move this first and that, and
that's like explore locally or something.
exactly. So it takes forever, and they had to decide the number of pi pulses, which was like 20 or so. While here we can go to like 1,000 spins, and then the number of pi pulses turns out to be 30, let's say. And it's much simpler. So
I'm just, yeah, I'm trying to organize this in part because, you know, the previous talk and some of these other things we were discussing. So if I wanted to view this as a spin glass and quantify just how hard it is to solve the problem using, available state-of-the-art
Yeah.
competitive algorithms, I would really have to discretize first and write it as a spin model and give it to somebody.
Yes.
And say, can you use, what kind of a spin glass is it? It's kind of like very non-local, very.
It's very non-local and depends.
It's not really a spin glass that people have studied.
No, also because again, it's not extensive.
Yeah, well, yeah, so can we talk about that? Because, most spin glasses with all-to-all interactions, you have to put like 1/n's in the right places anyway.
Exactly.
So I'm not sure, when you say not extensive, is it because of the?
Because this looks like delta t squared. And this goes like delta t in the log, which means that it's order 1. So this means that there is an optimum delta t, which minimizes this thing, which depends on how many, roughly speaking, how many zeros H has. How many pi pulses you want to do is order magnitude of how many zeros H has. And if you discretize more than that, it doesn't really matter.
Real.
So there is a physical scale here.
That's fine, yeah. But
And-
H, since H, we can design. The intuitive sort of number of spins should be proportional to T. Like if H has a
Yes.
reasonably regular pattern, you should say that, well.
It should be proportional to total experiment
Total,
time
yeah.
divided by the period of
The period of H, yeah, that's right.
more or less.
Times 10 to give it more wiggle room.
Sure,
Whatever.
exactly, yeah.
Yeah, so but if you do that, yeah, I guess, yeah, okay, I guess the short answer is that this is not, you call it a spin glass very colloquially because you know that these people spend days and days trying to find the minimum.
Yes,
But like, if you actually wanted to understand whether this is one of these things which is like, basically, does this have an entropic barrier?
yeah, so
I mean, is that
exactly.
the interpretation?
So the
or is
interpretation,
it-
I mean, I didn't even write it in the paper, but the entropic barriers maybe are there, maybe are not, but what we found numerically was that simulated annealing got stuck somewhere
Right,
and was clearly imposing more pi pulses than than eventually would do.
okay,
So if you plot the number of pi pulses, it looks something like this. Like the energy there. So the number of pi pulses was something that was, got stuck in this entropic
right.
thing. And then the system realized, oh, actually, forget, I can get
We
rid
don't-
of all of these
yeah,
things
that's
and
great.
then go down.
Yeah.
Okay.
there's
So
some intuitive-
it's just intuition. It's not really.
But I guess starting from the other end where you actually have control, theoretically, the spherical model. That has a unique solution.
That has a
And
unique
so that
solution.
suggests that if the physical problem is close to the spherical map model, then that gives you an idea that the solution is unique. Now, of course, if you did the 2 subdivision and 3 subdivision and you found that the corrections are big, you would say, well, maybe I don't trust this.
Exactly.
Yeah.
Instead the corrections were a few percent.
Yeah. So do you understand how to break it? How to make the corrections big? Like what kind of H of T would break it? Or what kind of J of T would break? I guess that would be kind of like an interesting question. To actually have a genuine glassiness. All right,
I don't know. I haven't thought about it.
yeah, because
honestly.
that would require kind of like looking in detail at the first corrections.
Yeah. Okay, maybe you really need like a lot of zeros in H of T.
Or a different JFT. I'm
Or a
curious
different-
about the properties of JFT that would break it.
Sure.
Yeah.
Sure. There's one way in which, there's a practical way in which this thing could be. That's why we looked at we used the Raspberry Pi, right? Because we wanted this step to be as optimized as possible. Because what I really would like to do is real time. adaptation, these are going to H of T. Because this
Feedback, yeah, yeah.
feedback, yeah, because this assumes that I know H of T, but in practice, you don't, right? You have an idea of what the frequencies are. So in practice, what you would like to do is a feedback. So you measure, okay, you do like a measurement and
Assuming a certain.
assuming a certain H of T, okay, and then you change it, assuming some properties, statistical properties of H of T, and then you change it. And then you, okay, so this would be really cool, and having already this step working at, you know, taking
So I'm curious.
milliseconds.
In the experimental data, they stop. You would think that with this continuous corrections, you can run the experiment forever. Until that curve turns over. They
Right.
stop the experiment before the curve turns over.
Well, there are other things that enter in the experiment, right?
Oh.
There is not only the coherence, there is also
Relaxation.
relaxation, there is yeah. So there are the things. I guess Santiago told me that they could go a factor of 2 of time, not much more than that.
I mean, that might be interesting, because that's a real physical effect you might actually.
Yeah.
You can capture from your
Yes.
stuff. Cool, all right. Okay, the food is not here yet, but I don't have any more immediate questions. So this was not complex at all.
Yeah.
Advertising.
Well, okay. It's a statement about the complexity. It's not,
Well,
not
it's a statement that
complexity.
if you can do math, sometimes complexity is just a computer science.
Sure.
Artifact.
Yeah.
It's like, what's the, since you're quoting, Katz,
Be
was it
wise, discrete.
Weinberg, you can use any coordinates you like, but if you use the wrong ones, you'll be sorry.
Yes.
Is that Weinberg? Oh, sorry, there's a question. Oh, please stop.
No, this was before.
Okay, all right, any questions from online people? Guess not. All right, we can,